Welcome back to Bot Thoughts by AmTalkSoft. I'm Alex. 2 years ago, the answer to almost any AI engineering question was the same, just called GPT-4. The bigger model wins. Today, that conventional wisdom is cracking. Microsoft, Google, and Meta have shipped small models that punch absurdly far above their weight, and the economics of running them yourself have flipped. Joining me is Sam. Sam, what changed? Why is 2026 the year that small language models stopped being a research curiosity and became a real architectural choice?
A few currents converged. First, the models themselves got dramatically better. Phi-4 from Microsoft, at 14 billion parameters, beats GPT-4 on math and reasoning benchmarks. Gemma 3 from Google ships in a 4B variant that runs on a phone and handles tool calling competently. Llama 3.370B is open weights and matches GPT-4 class quality on most tasks. Second, the inference stack matured. vLLM, Llama, CPP, and Ollama made local serving boring, meaning predictable and fast. Third, the cost story flipped. A team that's spending $50,000 a month on OpenAI for a workflow that's mostly classification and routing can run that same workflow on a single H100 for $3,000 a month. The math finally favors small.
Let's anchor terminology. When we say small language model in 2026, what size are we actually talking about? The line keeps moving.
2 years ago, a small model meant under 7B parameters. Today, the practical ceiling has shifted up. I think of 3 tiers. Edge models, under 4 billion parameters, runs on a phone or a laptop CPU. Phi-4 Mini, Gemma 3.4B, QN 2.53B fall here. Workstation models, 7 to 14 billion parameters, runs on a single consumer GPU like an RTX 4090 or 5090. Phi-4 14B, Mistral Small 3, Llama 3.211B server class small. 30 to 70 billion parameters, runs on a single H100 or 2L40S, but still small relative to the trillion parameter frontier models. Llama 3.370B, QN 2.572B, DeepSeek V3 Chat. All of these are small relative to the Claude Opus or GPT-5 frontier, but they are not small in capability.
Phi-4 keeps coming up. What's actually special about it? Microsoft has been on this small model thesis for years.
Phi-4 is interesting because of the data, not the architecture. It's a fairly standard transformer at 14B parameters, but Microsoft trained it on what they call textbook-quality data. Synthetic chains of reasoning, curriculum-structured math problems, code with detailed explanations. The result is a model that punches far above its weight on tasks that benefit from reasoning. On the GPQA Diamond benchmark, Phi-4 scores 56.1, beating GPT-4o's 50.6 in a model 1/10 the size. The trade-off is that Phi-4 is narrower. It's excellent at math, coding, and structured reasoning. It's weaker on conversational warmth, creative writing, and broad world knowledge, exactly because the training data was curated to be educational.
Gemma 3 is the other one I hear teams piloting. What's the case for it over the Llama or Mistral families?
Gemma 3 ships in 1B, 4B, 12B, and 27B sizes, and the 4B is the genuinely interesting one. It handles 128K context, supports tool calling out of the box, runs on a single 8GB GPU comfortably. Google trained it with the same techniques as Gemini, so it inherits some of the multilingual and instruction-following strengths. The license is permissive enough for commercial use. Where I'd reach for Gemma 3 over Llama 3.3 is when I need a small model that does function calling reliably for an agentic workflow on a constrained device. Where I'd still pick Llama. Anything where you want the largest open weights ecosystem, fine-tuning recipes, and community-tested quantizations.
Let's get prescriptive. When should a team actually pick a small model over a frontier API? What workloads make that switch obvious?
5 workloads where small wins outright. First, classification and routing, labeling tickets, routing customer messages to the right team, intent detection. A 7B model fine-tuned on 1,000 examples will match GPT-5 quality at 1/50th the cost. Second, structured extraction, pulling fields out of invoices, parsing logs into JSON. The task is constrained enough that a small model with tight prompting performs reliably. Third, RAG generation when retrieval is good. If your retriever is doing the heavy lifting, the LLM just needs to summarize and synthesize, and a 14B model handles that fine. Fourth, code completion in IDEs, cursor, and continue ship with local 7B models for a reason. Fifth, anywhere you need predictable latency. Local inference under 100 ms is a feature you cannot buy from a remote API.
And the inverse. When does going small bite you? When should a team stay with the frontier?
Open-ended creative tasks, long multi-step agentic workflows, and anything that benefits from very broad world knowledge. A small model writing a marketing campaign or doing competitive research will produce technically correct output that feels lifeless. Anything where the LLM needs to plan over 20 tool calls, small models lose coherence around step 10 or 11, and anything where freshness matters. Frontier models are continuously updated. Your local 14B is frozen at training time. If your application needs to know that yesterday's earnings report came out, no amount of small model fine-tuning fixes that. You either need RAG or you need a hosted model with a recent training date.
Walk me through the local serving stack. A team commits to running a model in production. What does the actual deployment look like?
For server-class deployment, vLLM is the default. Continuous batching, page detention, OpenAI-compatible API endpoint. You point an existing OpenAI client at it and most of your code keeps working. Hugging Face TGI is a strong alternative. For cost savings, run quantized weights, AWQ or GPTQ at 4-bit gets you 70% of the memory savings with 95% of the quality. Run 2 replicas behind a load balancer for high availability. Monitor latency at P95 and P99 because tail latency is what kills agentic workflows. For laptop or edge deployment, Ollama is essentially Docker for LLMs, pulls a model, exposes a REST API, handles GGUF quantization. llama.cpp underneath if you need raw control. MLX on Apple Silicon if you're targeting Macs. The ecosystem is dramatically more boring and reliable than it was a year ago.
Fine-tuning. There's a long-running argument about whether you should fine-tune or just prompt better. With small models, where does that come down?
For small models, fine-tuning is much more often the right answer than for frontier models. 2 reasons. First, the cost is real but bounded. A LoRA fine-tune of a 7B model on 1,000 examples runs in 2 hours on a single A100, costs maybe $40. Second, small models benefit more from task specialization because their pretraining is thinner. A LoRA-tuned 7B llama on your support ticket data will outperform an untuned Phi-4 by a meaningful margin. The toolkit converged: unsloth, axolotl, hugging face, PEFT. You write a YAML config, point it at a JSONL file of training examples, walk away for 2 hours, and ship. The hard part is curating the training data, not running the training.
Let's do real numbers. A team is sending 100 million tokens a month through a frontier API. What does the cost comparison look like if they migrate to a self-hosted small model?
Rough numbers for late 2026. 100 million tokens through GPT-5 at roughly $5 per million blended is $500 per month, which is fine for that volume. Now go to 1 billion tokens. That's 5,000 a month at the API and growing linearly. Self-hosting a Llama 3.370B on a single H100, you're paying $2 to $3 per hour reserved, around 2,000 a month for the GPU, and one H100 can serve roughly 3 to 5 billion tokens monthly at reasonable concurrency. So the crossover is around 600 million tokens a month. Below that, hosted APIs win on convenience. Above that, you'll probably save 50 to 70% by self-hosting. Add fine-tuning quality benefits and the break-even shifts even earlier. The actual decision is rarely cost-only. It's about latency, data privacy, vendor lock-in, and whether you have an ops team. But the math has crossed over for many enterprise workloads.
On the edge, phones, laptops, embedded devices, what's actually shipping in 2026? This was vapor for years.
It's not vapor anymore. Apple Intelligence ships with on-device 3B models for summarization and writing tools, with cloud fallback to a private compute cluster for heavier tasks. Google's Gemini Nano runs on Pixel devices for live translation and call summarization. On laptops, Microsoft's Copilot Plus PCs run a local 7B model for the rewrite and summarize features. The Snapdragon X Elite NPU and Apple's M4 neural engine make this practical without thermal throttling. The pattern that's emerged: small model on device for latency-sensitive features, frontier model in cloud for hard requests, with a router deciding. The user shouldn't have to know which is running. That hybrid architecture is the realistic 2026 deployment shape for AI features in consumer products.
What surprises teams when they actually try to run small models in production?
3 predictable surprises. First, prompt portability. A prompt that works great on Claude often fails on a 7B llama because the small model doesn't follow instructions as reliably. You need to retest your entire prompt library and often add few-shot examples that weren't necessary for the frontier model. Second, evaluation. You can't just run the same eval set you ran on GPT-4 and expect the small model to pass. The failure modes are different. Small models hallucinate more confidently, drop instructions in long contexts, and sometimes produce subtly wrong JSON. You need new eval sets that target small model failure patterns. Third, ops surprise. Running your own GPU fleet means dealing with driver updates, OOM errors, model version drift, replica scaling. Hosted APIs hide all of that. Budget for a half-time SRE if you're running production inference.
Final take, Sam. Engineering leader is listening on their commute. One concrete experiment to run this week to see if small models matter for their team.
Take your highest volume LLM workflow, usually classification, routing, or extraction. Pull 1,000 recent input-output pairs from your logs. Run them through a local Phi-4 or Llama 3.370B via Ollama on a laptop. Compare accuracy and latency to your current Frontier API path. If accuracy is within 5%, you have a real cost-saving migration on the table. If accuracy gap is bigger, you have data for a fine-tuning project. Either way, you've replaced a vague debate with concrete numbers. 2 days of work, and you'll know whether small is real for your specific workload, or whether the frontier still earns its price.
That's the playbook. Subscribe to Bot Thoughts wherever you get your podcasts. Support the show at buymecoffee.com/AmticSoft. Next episode, we're getting into AI red teaming, how attackers are actually probing language models in production, and what defenders are missing. Thanks for listening to Bot Thoughts by AmTalkSoft.